Okay. Howdy, guys. So, this is our second day of Calc 2, Section 2. Today we're going to do a few things. We're going to talk about section 6.1, which is on areas between curves. Which will also give us a little bit more opportunity to practice our substitution techniques. And we're also going to talk a little bit about office hours. So let's knock out the office hour thing first. Here's where I'm at. So the yellow stuff is for sure going to be regular drop-in office hours. And this orange stuff, I'm still floating around different ideas. I think somebody wasn't able to come unless it was early, like around 8. And since I teach from 8 to 9 Monday, Wednesday, and Friday, that left me only these options. And then I also had someone who was unable to come anytime before 5. So that left me with those same 2 options here. What I'm thinking I will do is probably this. I think this is probably how we're going to run it. So on Tuesdays, I'll do the early office hour. On Thursdays, I'll do the late office hour. And then Monday, Wednesday, and Friday, we'll have a mid-afternoon office hour, and then I'll also do the 12 to 1s on Tuesday and Thursday. I may not do these every week. I may reach out to those people who specifically needed them and only do them on the weeks that those people are available, because both of these are quite a big stretch in terms of like time between when I have other things to do there. But for sure, the yellow ones. So I'm going to be updating our Canvas page and our syllabus with the yellow office hours today. And that means if you want to, you can come by our first office hour today, 3:30 to 4:30, if you have any questions or problems you want to work on or anything like that. So that is the office hour situation. I'm going to refill my water here. And while I do that, I would like you guys to look at your schedule and just double check to make sure everybody can attend at least one of these per week. Okay, so take a look at your schedules. I know they're still coming together. See if there's anybody who couldn't make at least one per week. Be a good boy, Nova Katie. Okay. So before I proceed, is there anybody who could not attend at least one of these hours every single week? Somebody for whom none of these work? So everybody's capable of attending at least one? Okay, okay, good. Yeah, I do appreciate, even if the affirmative answer seems unnecessary, it's nice for me to know that you guys can hear me. So I appreciate, yeah, thank you, thank you. Okay, cool. So today we're going to talk about areas between curves, which is section 6.1 in your textbook. Calc 1 is supposed to cover this, but usually does not. So I'll remind you, the definite integral from a to b of f of x dx. This measures, this is an x. This is the signed area under the graph y equals f of x from x equals a to x equals b. All right, this old chestnut. So the question we ask in section 6.1 is, well, what if I have two curves? How do I find the area between them? Say y equals f of x is one of them, and y equals g of x is the other. So that my picture looks, and for now, I'll assume that f and g don't cross. Maybe here's f, maybe something like here's g. And maybe I want to find the area between them from a here to b here. So normally I do this on a board and I do this with multiple colors. The area I want is the area here in the middle. I don't want to measure this stuff down here. So let's imagine that I integrated just f. The integral of f would give me all of this. And that's actually a good start because that includes the area I want. So to get the area I want, I then just need to throw away the stuff on the bottom here. So if I start with the integral of f, and then I throw away all this stuff down here, I'll be left with what I want. I want it, right? This is what I want. So I start with the integral of f, which is all of the shaded area, the stuff that's like this. And then I throw away the integral of g. And what you'll find is that you can actually combine this into a single thing. So the area between f of x and g of x, and this is assuming f is above g, this is equal to the integral from a to b of f of x dx, that's the left hashed area, minus the integral from a to b of g of x dx, that's the black right hashed area. And you can write this as a single integral because the bounds are the same. So this is the integral from a to b of f of x minus g of x dx. And that's very nearly the whole story. The only catch here is if f and g happen to intersect and trade places. You know, one is above sometimes and the other one is below some of the other times. That's the only way this can go wrong. And the way you handle that case is just by splitting it up into a bunch of things like this. So more generally, the area between f of x and g of x from x equals a to x equals b this is the integral from a to b of the absolute value of f of x minus g of x. And this formula, this is what's given in the textbook. But it's not super duper useful because I bet most people don't know how to handle the absolute values, right? Integrating absolute value functions, usually you treat them piecewise and you split them up. And that's exactly what we'll do here. So to get rid of abs value, think of it as upper minus lower. So if f and g happen to trade place, f minus g is going to be positive if f is above g. But if f is below g, then f minus g would be negative, and so the absolute value would fix that and make it positive. That's the idea. In practical terms, the way we handle this, oh, sorry, I've got an alarm going off in another room here. I'm going to have to go handle that. In practical terms, the way we handle this is like this. Maybe here's my function f, and maybe here's my function g. And you see they trade places here. So maybe I say, here's A, here's B, and I want to find the area in between them. Part of the time, F is the upper, and part of the time, G is the upper. So what you have to do is find this intersection point here, this place where they crossed. You'll integrate from A to C, the upper minus the lower, which there is F minus G. And then you'll integrate from C to B, the upper minus lower there, which is G minus F. So here the area between F of X and G of X, this is equal to, it's still the integral from A to B absolute F minus G. But to get rid of the absolute values, we split the integral up into places where F minus G is positive, that's places where F is above G, and places where F minus G is negative, that's places where F is below G. So from A to C, from here to here, F of X, this guy, is above G of X, this guy. So you integrate the upper minus the lower in each region. But then from C to B, G of X is the upper. So it's this picture down at the bottom here. This is the formula they give you in the textbook. And in situations where F and G trade places, go from upper to lower, lower to upper, this is how you break it down. This is how you get rid of the absolute values. Because the absolute value of F minus G is either F minus G itself or the negative of F minus G, which is G minus F. Questions about the setup here, what it is that we're going to be finding, or why the formula is what it is? Nope. Okay, then let's get to it. Let's try an example. My favorite first example of this stuff is to play with sine and cosine. So e.g. exemplis gradi, or for example, many examples exist. Find the area between f of x equals sine x and g of x equals cos x from x equals 0 to x equals pi over 2. So always on these problems, the first thing we should do is sketch the graphs, right? Knowing how to set up the integral, which one is the upper, which one is the lower, all that stuff comes from looking at the picture. So your graphing skills need to be strong. You need to remember what the graph here of sine and cosine look like. So I'll start by drawing the graph of sine. Sine, we know, starts out at the origin and pokes its way up. I'll mark maybe here as 1. And I'll mark maybe over, I'll call this pi. I'll call this pi over 2. Sine of pi over 2 is 1. So we know it's a little too high, something like that. So it's going to come out here and look like this. And then we know sine comes back down over here at pi. And it continues on as that wave. But I'm just zooming in on this one piece. There's my point at pi over 2, comma 1. Cosine, I know, starts out at 1 and then dives down. Like this. And then he continues over here. Cos of pi is all the way down at -1, something like that. But the area I'm interested in is between 0 and pi over 2. So I want to take this area together with this area. That's what I'm looking for. This guy is sine. And this guy is cosine. Right? So my task is to find the shaded area. And you notice that just like we talked about on that last page, these guys do trade places, right? We start off with cosine being above sine. And then here, at this point, they switch, and sine is above cosine. So we need to find this intersection point where sine and cosine are equal to each other. So I ask you guys, where between 0 and pi over 2 are sine and cosine equal to one another? Yeah, good, pi over 4. So I know that this intersection point here has to be pi over 4, and we know that from our unit circle. So then I'll set up 2 integrals. One will go from 0 to pi over 4, and that will have this upper minus this lower. The upper here is cosine, and the lower here is sine. So this will be cos x minus sine x dx. And then my second integral will run from pi over 4 to pi over 2. And that'll be looking for this area. Here my upper is sine and my lower is cosine. So this one will be sine x minus cos x dx. And pay attention to how I'm writing my integrals. When I've got 2 chunks kind of separated by addition or subtraction, I always put them in parentheses, because that's the way the dx piece works on them. If you had to make a substitution, you would have to think of this as like distributing. So I encourage you to write things the way I write them. I try to model really good notation for you guys. So putting your integrands in parens like this is a wise move if they have more than one piece. How do I solve these integrals? What do I need to do?
Don't you have to integrate the functions and then like plug the b and the a in?
Yeah, good. We're going to use the fundamental theorem of calculus. So I need to find an antiderivative for cos x minus sine x, and then I'll evaluate that between 0 and pi over 4. And I'll do the same thing here. So an antiderivative for cos x minus sine x, I can think of each of these on their own. Who differentiates to become cosine? Oh, that's sine. The derivative of sine x is cos x, so sine x is an antiderivative for cos x. And then this minus is this minus. An antiderivative for sine. Oh, well, the derivative of cosine isn't sine, it's negative sine. So this would be minus negative cos x, like that. And this will be evaluated between 0 and pi over 4. So that's my first integral. And then my second integral, this will be plus, and I'll have another bracket here. Antiderivative for sine is negative cos. This minus is this minus. An antiderivative for cos is sine. And this piece gets evaluated between pi over 4 and pi over 2. Now, for my money, it's worthwhile taking this minus minus here and making that a plus. Let's go ahead and plug in. So this is sine x plus cos x. When I evaluate at pi over 4, this will be sine pi over 4 plus cos pi over 4. And then I subtract what I get when I plug in 0. So that will be sine of 0 plus the cos of 0. All right, that's my first bracket. All this is this. So I need to add to that what I get from the second evaluation bracket stuff, which is negative cos pi over 2 minus sine pi over 2 minus what I get when I plug in the lower bound, pi over 4, which is negative cos, oh, and I'm running out of space here, pi over 4 minus sine pi over 4, like that. And each of these are known things. All of these are nice. The sine of pi over 4 and the cos of pi over 4, those are both root 2 over 2. Minus the sine of 0 is 0, the cos of 0 is 1. And then over here, negative cos pi over 2. Well, the cos of pi over 2 is 0, and the sine of pi over 2 is 1. So this is 0 minus 1 minus negative cos pi over 4. Well, that's negative root 2 over 2 minus the sine of pi over 4 is root 2 over 2 also. And I suppose in theory you could stop here. Just for the record, a common question, like what do I expect out of you guys on exams? I would not be okay with you stopping here. You got to show me that you know these things, right? You got to show me that you know your unit circle. So what is the cos of pi over 4? What is the sine of 0? All that shit you got to plug in. But if you were time crunched on a test or something like that, then I would be okay with you stopping here. However, you can clean this up quite a bit more. So let's do that. It's not hard. Root 2 over 2 plus root 2 over 2 is 2 root 2 over 2, or just root 2. So this is root 2 minus 1 plus, this is negative 1 minus, this would be negative root 2. So altogether I get root 2 minus 1 plus root 2, which is 2 root 2 minus 2. That's not bad. Sorry, forgive me. See me eating breakfast here. Okay, any questions about any one of these steps? Let's start with setting up the integral. Any questions about how we go from the picture to the integral we started with here? Whatever you're thinking, I'd like to hear it. Okay, any questions on the antiderivative step? So any questions on passing from this to this? Yeah, I see something in the chat here. No? Oh, okay, cool.
Question. For the antiderivative, isn't it just like the derivative of the derivative?
Not necessarily, no. Sine and cosine happen to cycle through derivatives, but most functions don't do that. And it's true that the second derivative of sine or cosine is equal to the negative of the original, but you have to think about going backwards on the differentiation chain. So you have to ask who has, for example here, I have to ask who has cosine as his derivative. And there I think about it for a minute, who differentiates to become cosine? Oh, sine, the derivative of sine is cosine. So sine is an antiderivative for cosine. When I come to this guy, I have to ask who differentiates to become sine. And the answer there is not the derivative of the derivative. That would be sine itself, or negative sine. But here I have to ask who differentiates to become sine. I think, oh, well, the derivative of cosine is negative sine x. So then the derivative of negative cos x, that would be sine x. So that's where this guy comes from.
Cool, thank you. Yeah, I'm definitely gonna have to practice that a little bit more, but makes sense, so thank you.
So in the textbook, if you go back to section 4.9, yeah, they introduce the notion of an antiderivative, and they give you lots of examples. This table is definitely a place you should be comfy working. Don't worry too much about the hyperbolic trig, but definitely the regular trig and all the other stuff we got in no cold. And then another place to look to remind yourself or review, I think is, yeah, I think here in this section they have, yeah, this is a good place. So everybody in this class should know everything in this table up to here cold. If that stuff didn't sink in Calc 1 or it like sunk in, but then it kind of floated away over the last week, that's understandable. But we got to come back and make sure we know all this shit like rock solid.
You got it, thank you.
Of course. Okay. Let's play with some more examples. One of the big challenging parts in this section, and the few sections we're going to cover after this, 6.2, 6.3, next week on volumes, is just drawing the picture, right? Having a large enough library of graphs in your head that you can draw a pretty good picture from memory. Now, if your memory isn't perfect, you can use Desmos a little bit, but on the exams, it'll be crucial that you're comfortable drawing graphs yourself, and I will make you do that. So let's go through something kind of fun like that. Let's find where the picture isn't so obvious. Let's find the area bounded by. Bounded by just means like contained within a closed region of y equals 1 over x, y equals 1 over x squared, and the vertical line x equals 2. So what does 1 over x look like? What does the graph of 1 over x look like? Okay, well, 1 over x, I remember him. At 0, he blows up to infinity, and he's kind of got this like curvy shape here. Something like that, right? That's y equals 1 over x. I know it goes through the point 1, comma 1. And then what about 1 over x squared? Well, x squared, if x is bigger than 1, then x squared is definitely bigger than x. So everywhere to the right of 1, this guy should be underneath this guy because his denominator is bigger than this guy's denominator. So overall, he'll be smaller. But everywhere to the left, x squared, if you take a number like 1/2 and square it, if you take a number between 0 and 1 and square it, the result is larger than the number itself. So 1 over x squared starts out above. I'm going to butcher this picture, but I'll do my best here for you. But then he dives down towards the x-axis much faster as you start wandering off to the right. Okay, so here's y equals 1 over x squared, and here's y equals 1 over x. Now, if you don't remember these well enough, you could always make a table to get at the graph. I'm also okay with you using Desmos from time to time to help you with graphs. They do both have vertical asymptotes at 0. That's true. So you'll see here, both of them blow up at 0. But we're interested in what's happening over here. So the blue, that's 1 over x squared. You see, he starts off above 1 over x, but then to the right, he starts settling down on his horizontal asymptote much faster. 1 over x has the same horizontal asymptote, the same vertical asymptote, but he doesn't settle down on his horizontal asymptote quite as fast. So you see from there to here, very similar. I mean, your pictures don't have to be perfect, but they have to be good enough for you to tell what's going on. So I'll mark this as x equals 2. And here's x equals 1. So the area I'm looking for, the area bounded by these guys, is this. All right, the line x equals 2 is a vertical line here. So this is the area I'm after. And I can get it by integrating the upper function minus the lower function from x equals 1 to x equals 2. So my area is kind of think of it in terms of this mnemonic. My upper function there is 1 over x, and my lower function there is 1 over x squared. So then I turn to you guys and I ask, okay, how do I evaluate this integral? I need antiderivatives, right? And it's actually a different rule for 1 over x and for 1 over x squared. So you might want to think of splitting this up as the integral from 1 to 2 of 1 over x dx minus the integral from 1 to 2 of 1 over x squared dx. And then I'll come down here. Very good. Yeah, Davis has it. An antiderivative for 1 over x is the natural log of the absolute value of x, and you want to be a little bit careful. So that first piece has antiderivative ln abs x, and we evaluate from 1 to 2. And then this minus is this minus. An antiderivative for 1 over x squared, you think about it as a power rule thing. That's the same as x to the negative 2. So if you add 1 to that power and divide by that power, you get negative x to the negative 1, or negative 1 over x. And you have to evaluate that from 1 to 2 also. So remember this piece right here, we're thinking of as the integral of x to the negative 2 dx. So you'll add 1 to the power, gives you x to the negative 1, and divide by that new power. And then evaluate that from 1 to 2. The nicer way to write that is as negative 1 over x. So now we're free to do our evaluation. We always plug in the upper number and then subtract what you get when you plug in the lower number. So this first guy, the absolute value of 2 is just 2, so this is ln 2 minus the absolute value of 1 is just 1. So you get ln 2 minus ln 1. And then from that I'll subtract. If I plug in x equals 2 here, I get negative 1/2 minus, and then I plug in 1, I get negative 1. Like that. What is this guy? What is the natural log of 1?
Is it E?
The natural log of e is 1, but the natural log of 1 is, yeah, 0. So this is ln 2, and then here I'll distribute my negatives and stuff. This is negative 1/2 plus 1, which is positive 1/2 overall, and then the minus here makes everything negative again. So you get ln 2 minus 1/2, which is a pretty small number. ln 2 is like 0.6, so this is like 0.1. Any questions on this guy?
Why did we separate both the terms when we started integrating it?
You didn't have to. You could just say the antiderivative for this is ln x minus 1 over x, and that would work just fine. Or ln x plus 1 over x, I guess, 2 minuses making positive.
Mm-hmm.
So you could think about the rule for this and the rule for this separately, because this is a natural log, and this one you have to use the power rule. So because we use different rules to antiderive each piece, I wanted to split them up and let you think about each of them on their own.
Oh, okay.
But it's not necessary.
Thank you.
Yeah, of course, it's a good question. What else? What else are we thinking?
So it's okay to put the parenthesis, to change the absolute value back to parentheses?
As long as the thing you're plugging in is positive, yeah.
Okay.
Yeah, the basic idea here is just that if I plugged in a 2 here, I'd have ln of the absolute value of 2. But the absolute value of 2 is just 2, because 2 is positive. So ln of absolute value 2 is the same as ln 2. But either way would be correct. If you wanted to write the absolute values there, I certainly wouldn't take points off. And again, common question like, at what line can I stop simplifying? I wouldn't quite be okay with this because I need you to show me that you know that the natural log of 1 is 0. So I would want you to get all the way here, or at least include something like that to indicate you know the value of log 1. Okay, so in the situation where your functions are what they usually are, y equals a function of x, like y equals f of x or y equals g of x, just integrate the upper minus the lower. Maybe you have to split it up depending on whether your functions cross over each other or not. But that's not the only setting we care about. Sometimes your curves come where instead of having y as a function of x, x is a function of y. Sometimes we want to find areas of regions what if our region is bounded by curves like x equals f of y and x equals g of y. In that case, you really just kind of turn your head sideways. So maybe you have something like this. I'll call this f of y. And maybe you have something like this. And I'll call that g of y. And so the area here I want is like this region. To do this, you need to find your bounds as y values and set up the integral dy. So here you would integrate from y equals a to y equals b, your right function minus your left function. So the increasing x direction is this way. So if I want to measure the area in here, I would be thinking about having little Riemann rectangles in there that look like this. So the height of my little Riemann sum rectangles that I would use, if I was doing this as a Riemann sum, the height would come from this x value minus this x value, or the rightmost minus the leftmost. So just like in the normal case, you integrate upper minus lower, here you would integrate from a to b, and those are y values, the right function minus the left. And your integral would be done dy. This might seem like a trivial thing because if you just turn your head sideways, it becomes the same shit we've been looking at. Your right is your upper, your left is your lower. And you might ask, why the hell do we even care? The answer is because in 6.2 and 6.3, some of the volume problems that we'll be looking at, you have to think of in terms of dy integrals. So this is a place for you to practice getting comfy with dy integrals and setting regions up and drawing pictures where your functions are functions of y rather than functions of x. So here, in this particular problem, my rightmost function is the g function, and that's true everywhere in this region. So I would integrate from a to b, g of y minus f of y dy. Questions about the formula? Okay, let me grab an example from your textbook then. I have a nice one here. Yeah, let's do this guy. So y equals x minus 1 and y squared equals 2x plus 6. Let's x minus 1 or x plus 1? X minus 1. So let's find the area bounded by y equals x minus 1, and y squared equals 2x plus 6, yeah. Okay. So depending on how much time your pre-calc class spent on conic sections, you may or may not be able to see how this guy looks right away. But since it's the y that's squared and not the x, you know your parabola is going to open up sideways rather than up or down. And the question is, does it open to the left or does it open to the right? Since the y term here is positive, you know that he'll be opening to the right. That as your y's go up, your x's go up as well, rather than going down. First, let me solve both for x. So that first guy, y equals x minus 1, that's the same as saying x equals y plus 1. And the other guy, y squared equals 2x plus 6, that's the same as saying, let's see, y squared minus 6 over 2. So x equals 1/2 times y squared minus 6, like that. So here's like f of y, and here is g of y. I need two things. I need to know who's the right function and who is the left function. And I also need to know what are the limits for my integral? What are a and b? What are the two y values that determine the start of my region and the end of my region? For both of those, I need to draw the picture. I need a nice graph. So y equals x minus 1, I know what that looks like. That's a line with slope 1 and y-intercept -1. So he looks like this. Of course, this is my x-axis. This is my y-axis. This guy's a little tougher. You can look for the y-intercepts by asking where is this equal to 0. If I plug in x equals 0, then this guy will be 0 when y is plus or minus the square root of 6. You can ask how big is root 6? Well, root 4 is 2, so root 5 should be a little bit bigger than 2. Root 6 should be a little bit bigger than 2, but smaller than 3, right? Because root 9 is 3. So 1, 2, 3. Somewhere right around here is root 6. And 1, 2, 3. Somewhere right around here is negative root 6. And then you can also ask for the x-intercept. If you plug in y equals 0 here, then you get x equals 1/2 times -6, which is -3. So I'll mark this as 1, 2, 3. So there's my x-intercept. Here's my two y-intercepts. So I can draw my parabola. Yes, to look something like this. Okay, and I'll extend this line so we can see a little better. I'll bold this guy so he just looks like a point. Intersection point there, intersection point there. All right. So here's a pretty nice picture. These two curves. This top guy, or this parabola, is 1/2 y squared minus 6. And the line is x equals y plus 1. And so the region whose area I'm trying to find is this region. And the two things I need are the y values at those intersection points.
Excuse me, Professor.
Yes. Yes, go ahead.
What is the point on the x-axis on the left, on the negative side?
-3.
-3. Okay.
Yeah. So I got that by plugging in y equals 0 in this expression. If you plug in 0 for y, then x is 1/2 times 0 minus 6, which is 1/2 times -6, which is -3. And
Thank
this
you.
guy is √6. This guy is -√6. So then the numbers I need, my bounds of integration, are from here to here. But it's not clear what those numbers are. So to find the intersection points, what should I do?
Can you set the equations equal to each other?
Yeah, I set this equal to this, right? They're both already solved for x. So if I set them equal to each other, I will get y values out, and those y values will be the y values where these things smack each other. I set f of y equal to g of y. It doesn't matter which one you call f and which one you call g. I guess I'll call this f of y. And I'll call this g of y, just to be consistent. So that means I'll set y plus 1 equal to 1/2 times y squared minus 6. I can start by multiplying both sides by 2 to get rid of the 1/2, and I'll distribute the 2 on the left to get 2y plus 2. And on the right now, the 1/2 will be gone. I'll just have y squared minus 6. And then I can subtract all this shit over here to get 0 equals y squared minus 2y, and then minus 6 plus 2 is -4, right? Is that right? And then I need to think of solutions to this equation. Let's see, did I do everything right there? Yeah, this looks good. Okay, so we need to think of two numbers if we can, whose product is -4 and whose sum is -2. I'm not sure that two such integers exist.
Wouldn't it be -8 instead of -4?
Oh yeah, we're subtracting the 2. Thank you. I knew something looked fishy there. Thank you, thank you. And that will make these solutions much nicer. So I'll just write this here. This is a -8. Yeah, good catch. We're subtracting this over. So -6 minus 2 is -8. That's better then, right? Yeah, so we need two integers, hopefully, whose product is -8 and whose sum is -2. I think -4 and +2 work. So this is equivalent to saying 0 is equal to y minus 4 times y plus 2. So in other words, this guy down here, this is -2. And this guy up here is +4. So we'll be integrating from -2 up to +4. And I'll integrate the rightmost function, which is the one we've been calling f, minus the leftmost function, which is the one we've been calling g. And the integral is done dy. F of y is y plus 1. So this all continue over here. So that's the integral from -2 to 4 of y plus 1 minus 1/2 y squared minus 6 dy. So any questions on the bounds work or writing down this integral? Questions up to here?
So do you not include the -3 yet or at all?
Let me think. This -3 is not relevant for anything other than helping us draw the picture. So my integral is being done dy, so my bounds are going to be y values. I take the y value here for my lower bound and the y value here for my upper bound. Ask yourself, what's the smallest y value anywhere in this region? Oh, it's right down here. So
Okay.
that's going to be my lower bound. And what's the largest y value anywhere in this region? It's up here. I don't actually care about x values because I'm doing everything with respect to y.
Okay.
It's a good question though. What else do we wonder? Anything else on our brains here?
If in the problem, we see that there's no given x, like x equals 2, for instance, for the last example, does that mean we're going to be using dy, or is that just something that we should consider using?
Really, the answer to that is you have to draw the picture and ask whether your situation is one in which you can find the area using a dx integral or not. If I was just interested in the area to the right of this point, right, like so the shaded stuff that is included in my blue box here, I could set that up as a dx integral if I wanted to. But because I'm also including some of this stuff, this region cannot be found in terms of a dx integral, at least not without some very tricky stuff, because the formula, the function that defines the curve up here is the same as it defines the curve down here. And otherwise, in other words, this doesn't pass the vertical line test, right? This guy fails the vertical line test because a vertical line does hit him in more than one place. So the curve over here cannot be given where y is a function of x. It must be given where x is a function of y. And that's really what tells us that we're going to have to do the integral dy rather than dx. So the boundary curves that they give you, if x is a function of y, then you'll most likely be doing the integral dy. And if y is a function of x, then you'll most likely be doing the integral dx. But there are situations where you'll have to choose. And really the only way to choose is by drawing the picture and then imagining your little Riemann rectangles. Could I build a Riemann sum for this guy over here? No, because the height of this rectangle, let's see if I can get my pen in here. The height here of this rectangle would be coming from something like this, which can't be solved neatly for y. If you take square roots to try and solve that for y, you'll get a plus and a minus. In other words, this does not represent y as a function of x. It only represents x as a function of y, which is why we had to solve it for y and work the dy integral. So I would say draw the picture. Draw the picture and try to imagine little Riemann rectangles. Here my Riemann rectangles would look like this. So because the most natural Riemann rectangles here are left to right rather than up to down, I know that my integral must be done dy because this thickness here is like a dy thickness. Does that make sense?
Yes, thank you.
Okay, so then we're going to expand all this stuff out, combine all my like terms, find an antiderivative and evaluate. So this is integral from -2 to 4 of y plus 1 minus 1/2 y squared minus 1/2 times -6 is +3. And then I can combine the 1 and the 3. And I get integral -2 to 4. I'll write that in standard order. So that's -1/2 y squared plus y plus 4 dy. And now we're ready to take our antiderivatives. An antiderivative for y squared is 1/3 y cubed. So this will be negative 1/6 y cubed. An antiderivative for y is 1/2 y squared. And an antiderivative for 4 is just 4y. And that is all to be evaluated from -2 up to +4. And this 1/6 here, this is negative. Questions about the antiderivative step? I see something in the chat there. Feels good? All right. So then from here, I'll plug in my upper bound and then subtract what I get when I plug in my lower bound. At the upper bound, we'll have negative 1/6 times 4 cubed, that's 64, plus 1/2 times 4 squared, that's 16, plus 4 times 4, that's also 16. So here's what I get at my upper bound. And I'll subtract from that what I get at my lower bound, which is negative 1/6 times negative 2 cubed. 2 cubed is 8, so that's negative 8. Plus 1/2 times negative 2 squared. Negative 2 squared is 4. Plus 4 times negative 2. So that's what the evaluation step looks like. And then there should be lots of like terms that I can combine. Let's go through this carefully. I don't think 64 is divisible by 6. So I'll just leave that as negative 64/6 for now. And these guys are nice. This is 8. 8 and 16 is 24. Minus. Let's go ahead and just, no, we'll be careful. Okay, so first parenthesis group is here. Second parenthesis group I'll simplify and then we'll distribute the negative. So this will be negative 8 times negative 1/6 is positive 8/6. 1/2 times 4 is definitely 2. And this is a negative 8. So this will be a plus 2 minus 8 is minus 6. And then we can combine everything together. So I'll have 24 minus negative 6 is 24 plus 6, that's 30. And then I'll have negative 64/6 minus 8/6. That's negative 72/6. Okay. You don't have to worry about typing here in the chat. I got a log. Just make sure you use your actual name when you sign into Zoom. So any questions about the evaluation or the arithmetic that we do at the end to clean things up? Okay. So we have time, I think, for one more. Let's go ahead and attack one more fun one here. And let's do something that'll get us some practice with substitution. This is a problem I like a lot. Let's find the area enclosed by y equals ln x over x and y equals ln x all squared over x. These are two pretty interesting looking curves. Log x over x I happen to know, but log squared x over x I don't know off the top of my head. So we'll use a little bit of Desmos. Here's my x-axis, here's my y-axis. Log x over x has a problem, both of these have problems at 0. Here, the ln x wants to go down to -infinity as you get closer and closer to 0, but the x wants to send you out to +infinity. The ln actually wins. Ln x over x starts out down here, comes up, and then sort of smooths out. So we'll mark this as 1, comes up like this, comes up here to a max value, and then sort of chills out. And then eventually he'll turn around and start going back down towards the x-axis, but it takes him a while to do it. So he looks like this. That's y equals ln x over x. And this x-intercept here is at 1. One of the problems that I give my Calc 1 students often is to find this max. But we're in Calc 2, and we also need to graph log squared x. So let's do it. Here's y equals ln x over x. You see him there looking about how he does on our page. But what about the other one? There he is. He's doing something quite different. So log squared x, he comes down from above, just kisses the x-axis there at 1, he bounces off, and then comes over here, and somewhere to the right of the max for this, he intersects the green guy. So coming back, this guy, he comes down, then bounces here, and you have some sort of inflection point, and then continue off like that. This is y equals ln x squared over x. So the area we're looking for is this area. And you tell me, is this going to be done using a dy integral or a dx integral? Are my curves here functions of x or functions of y?
It'll be in relation to dx, right?
Good, yeah, these are both functions of x. So this will be a dx integral. My upper function in that region appears to be log x over x, and my lower is log x squared over x. I can tell from the picture that they touch here at 1, this is where that region starts, but I can't tell where this is. So I need to find the intersection points. So we're going to find the intersection points by setting them equal. So I set ln x over x equal to ln x squared over x. And in algebra and trigonometry classes, I always tell students, don't multiply both sides by x and cancel the x's from the bottom because you lose information. But as long as the x is not 0, you can multiply both sides and cancel, it's okay. And we know x equals 0 is not one of my solutions. Neither of these functions are defined when x is equal to 0. So I'll start by multiplying both sides by x and canceling those. We're just trying to get these intersection points out. So I multiply by x, that cancels, multiply by x, it cancels, and you get ln x equals ln x all squared. Which is a funny looking equation. You might not have seen a lot of equations like this, but if you just follow your nose, everything will come out fine.
What happened to get to ln x equals ln x squared?
I multiplied both sides by x.
Okay.
Yep, so then the x's cancel on both sides, and you just get this top is equal to that top. You could pull this over and have a common denominator. That would work also. But this is a little faster, a little cleaner. So from here, then I'll subtract ln x from both sides. So I'll have ln of x all squared minus ln of x. And from there, I can factor ln x on the left. I can factor ln x out on the right. So I'll have ln x times ln x minus 1. Everybody see how this factors like this? This is like u squared minus u. So I factor a u out and I get u times u minus 1. So those guys will be equal. Thus the two curves intersect when either, since here I have this product, ln x times parentheses ln x minus 1 is equal to 0, one of those has to be 0. So either ln x is equal to 0 or ln x minus 1 is equal to 0. This guy's easy. ln x is equal to 0 if and only if x is equal to 1. You exponentiate on both sides. You get e to the ln x equals e to the 0. E to the ln x is just x, and e to the 0 is 1. Here we have to add 1 to both sides. So you get ln x equals 1. And then you exponentiate on both sides. And you get x equals e to the 1, which is just e. So your intersections are at 1, and this guy over here is e. Everybody okay with that? Questions about how we solved this? So we cross multiply, cancel the x's. That gets us here. Subtract ln x from both sides. That gets us here. And then factor ln x on the right. This is ln x squared minus ln x. So that's ln x times ln x minus 1. And then we set each of these equal to 0 on their own. Ln of x is equal to 0 when x is equal to 1. And ln x minus 1 is equal to 0 when ln x is equal to 1, which means x is equal to e. So my area, these 3 dots arranged in a triangle mean therefore. So therefore, my area is equal to the integral from 1 to e of the upper minus the lower. And the upper in this region is ln x over x minus the lower in that region is ln x squared over x. And the integral is being done dx. What am I doing for time? Ooh, we're right at time. Okay, how do you solve this integral? I'm gonna ask you to hang out with me just for a couple minutes. I know we're a little bit over, but please, if you can, stay, be patient. Otherwise, you can see the problem finished in the YouTube video, which I'll post a little later today. But for those who can, tell me, how do you solve this integral? This is a pretty scary looking integral compared to the ones we've seen so far. Why is this integral scary looking? If there's a piece we could make go away, what would we make go away? I don't really care that the upper bound is E, but yeah, it's the natural log that makes this so frightening looking. Now check this out. This is the integral from 1 to E of ln x times 1 over x minus ln x squared times 1 over x dx. Everybody agree with that algebra? You see what's going on there? Dividing by x is the same as multiplying by 1 over x. Or having an x downstairs is the same as having a factor of 1 over x. And now this 1 over x is actually common to both pieces. So I can factor it. And that's convenient because that's precisely the piece we need to make the substitution u equals ln x go through. But I want to do that substitution very carefully, and I want you guys to play along with me. So this is ln x minus ln of x all squared times 1 over x dx. I factor the 1 over x. And now I can make the substitution u equals ln x. So I let u be the natural log of x. Then du, he's going to just be 1 over x dx, which is why it's so convenient to factor this. You also must change your bounds. When x is equal to 1, my old lower bound, which was an x value, if you plug in x equals 1 here, you get out u equals the natural log of 1. Natural log of 1 is 0. So when x is equal to 1, u is equal to 0. What about the upper bound? When x is equal to e, u would be the natural log of e. The natural log of e is 1. So when x is equal to e, u is equal to 1. So there's my little box with all the substitution stuff. Stay. Which means when I make that substitution, my integral will become the integral from 0 to 1 of ln x, well that's u, minus ln of x all squared, that's u squared. And then 1 over x dx, that's exactly du. So we've got to change the bounds. We've got to deal with the differential. It happened to be really nice because we did this algebra first. And then my integrand becomes a nice, neat polynomial. That's super easy. An antiderivative for u is 1/2 u squared. An antiderivative for u squared is 1/3 u cubed. And I evaluate between 0 and 1. So then plugging in the upper bound, 1, I get 1/2 times 1 squared minus 1/3 times 1 cubed. Plugging in my lower bound, I get 1/2 times 0 squared minus 1/3 times 0 cubed. This is all 0. So I just get 1/2 minus 1/3, which is 1/6.
So I have a question.
Yeah.
Why did we change the upper and the lower bounds again?
Because we're making a substitution. And anytime you make a substitution in a definite integral, in an integral with bounds, you have to change those bounds. These
Okay.
bounds were x values, right? If you look on the original graph, that was x equals 1 and x equals e. When you make a substitution, what you're doing is a coordinate transform. So you need to get new bounds for the new variable. So to get your new bounds, your u equals 0 and u equals 1, you take the old bounds and you plug them into the equation that defines the substitution. So I
Okay.
plug x equals 1 in here and I get u equals ln1. Oh, that's 0. So my old lower bound of 1 gives me a new lower bound of 0. And similarly, if I plug x equals e in here, I get u equals ln of e, which is 1. So my old upper bound of e gives the new upper bound of 1. And if we don't change those bounds, then this integral would not be equal to this integral. If I wrote this with the bounds of 1 and e, those would not be equal. I can justify this to you in a picture way. Let me go ahead and take care of Alex's question here. So the 1/2 and the 1/3 came from the antiderivative step. An antiderivative for u to the 1 is u to the 1 plus 1, or u squared, divided by 2. So 1/2 is the divide by 2, and 1 plus 1, that's the power here. So I increase the power by 1, and then I divide by that new power. So if I take this guy, his power right now is 1. If I increase that by 1, that'll become u squared. That's why this is squared. And then I have to divide by that new power. That's the 1/2. You could write it as u squared over 2 if you prefer. Let's take a quick look at why you got to change those bounds, because this is something that I feel is almost never addressed correctly in Calc 1. And let's look at it in a really simple example. Imagine I want to integrate from 0 to 1. Let's make it simpler. Imagine I want to integrate from, say, 1 to 2 of x minus 1 all squared dx. Yeah, I know this is a little bit trivial, but just think along with me. Here's x minus 1 squared. And the region from 1 to 2 is this region. If I wanted to make the substitution u equals x minus 1, du is dx, this should be equal to the integral of just u squared, because u is x minus 1, du is dx. Okay, so nothing weird there. But I integrate from where to where? So this is the x, y axis. What does u squared all on its own look like though? If I look on the uy axis, here's the graph y equals u squared. If I still went from 1 to 2, that would be like getting stuff over here, right? Maybe this continues like this. So you can see immediately that the integral from 1 to 2 of u squared is not the same as the region I'm looking for. I'm looking for the region from the vertex to 1 over. Really what I wanted was this dark shaded region. And in order to get that dark shaded region, I have to integrate not from 1 to 2, but from 0 to 1. And you'll see that if you plug in the old bounds, plug in 1 when x is 1, u is 0 because 1 minus 1 is 0, and when x is 2, u is 1. So this business where you plug the old bounds into the substitution, what that does is it accounts for how you're moving the graph around. When you make a substitution, it's called a coordinate transform, and it's not always as simple as shifting left or shifting right, but it can be. And I hope that this makes sense. In order to get this same area, which is this integral, as an integral of just u squared, you need to not integrate from 1 to 2. You don't want this shit. That doesn't even have the right shape. You want the stuff from the vertex over to the thing at height 1. That's this shit. So we have to change those bounds. If that justification doesn't sit entirely well with you right now, that's okay. From the standpoint of the class, what I need you to remember is that anytime you make a substitution in a definite integral, you always must change the bounds. And the way to change the bounds is to plug the old bounds in for the old variable, and whatever your substitution is, whatever equation defines your substitution. So here the substitution is u equals x minus 1. So I plug in my old bounds for x. When x is 1, u is 0. When x is 2, u is 1. And I discover that this new guy needs to be integrated from 0 to 1, not from 1 to 2. And in this case, the coordinate transform was just a left shift, but they can be much more complicated. You'll learn about these in great detail, exactly what coordinate transforms mean and how they affect integrals in Calc 3 when you talk about the Jacobian determinant. But this is what's called a coordinate transform. And so the old bounds don't work in the new coordinates. All right. So I think we're a little bit over time. That's where we're going to have to leave it for today. I'll remind you, I do have an office hour from 3:30 to 4:30 today. You're welcome to come by and hang out, ask some questions, work on some problems, whatever you'd like. Of course, you do have homework in WebAssign right now. That is, sorry, this is an old class. You guys are right here. So you've got this homework to be working on, and it is due next Monday. So please, don't put this off. Don't wait for the weekend to do this. There's a good amount of work here. On average, the homeworks will take about 3 hours each week. So we got to start dumping that time in. You don't need to say here. I've got a way of logging everybody who comes in and goes, so don't stress that. But if there are any last minute questions, now is a good time for those before we sign out. Anything that's bugging us or we want to talk about before we go? So Krishna, I'm still figuring out exactly what the office hours will be, but right now, these yellow ones are the ones I've decided on for sure. So Monday and Wednesday, we'll have an office hour from 3:30 to 4:30. Tuesday and Thursday, we'll have an office hour from 12 to 1. And Friday, we'll have an office hour from 2 to 3. And I'll be updating the Canvas page today with links to that standing Zoom office hour. And then I'll also be throwing in some of these guys, but I'm not sure exactly when. It's going to depend on when they're needed. Because these are for folks who could not make any of the yellow ones. So I'll most likely be doing these, but maybe not every single week. Good questions. I definitely do want you guys coming to office hours. I want to be able to talk with you and see your work and see how things are going. Anything else that we're wondering about right now? Okay then, so I'm going to go ahead and sign off here for today. Remember, if you want to talk, Canvas or office hours are the way to go. Either send me a message or just drop in. The link to the office hour will be up in a little bit. I hope you guys have a lovely rest of your day, and I'll see you on Friday.